So we'll continue with our class today. So we'll start with serial transmit and receive. So serial transmit or receive means serial data transfer, and serial means bit by bit data transfer. That means one bit at a time, and then once you complete first bit, you go to the second bit and so on. So that's serial transmit and receive. So there are several serial communication protocols which are available in modern microcontrollers, and one of them is UART, which is Universal Asynchronous Receiver Transmitter. So serial means I only refer to RT, and UART means Universal Asynchronous Receiver Transmitter. So this UART communication uses the following lines. Look at the figure which is shown at the upper part of the slide. So there are two devices, 1 and 2. So these are mainly microcontroller devices. And now there are 3 pins out of several other pins in between these two microcontrollers. We are only using 3 pins to connect between each other. Okay, so device 1 or microcontroller 1 is having 3 pins which are useful for serial communication, which are ground, TX which is transmit, RX which is receive. And on the other side, device 2, the microcontroller 2. So again, 3 similarly named pins are available. So which are ground, TX and RX. Now the connection between the ground terminal should be shorted on both the devices. It's not necessary VDD or VCC signal should also be shorted. So VCC and VDD can be completely different. That means device 1 may have battery 1 to power up, device 2 may have a AC power adapter or battery 2 to power up separately. But ground should be connected for a common reference. Okay, so as you understand through circuit analogy. Now, looking at the TX and RX, so TX is the transmit pin, which is the output pin for a given microcontroller, and RX is a receive pin, which is an input pin for a microcontroller. So output TX from one microcontroller, device 1, is connected to input RX of the second microcontroller, and vice versa for the other 2 terminals. Like output TX from the second microcontroller is connected to the RX1 input of the first microcontroller. So this crisscross connection is important for UART, and this is a dedicated hardware connection. That means there are wires, physical wires, or some sort of conductive path between the lines, as shown over here. Now, serial communication, so there are few questions. So why do we need serial communication? So serial means bit by bit. That means more time is required because you cannot send multiple bits at a time. So there's a problem with timing. It is slow. But the advantage is the number of hardware connections which are required the number of hardware lines or the connection wires which are required to connect between the devices is actually minimal or reduced as compared to parallel. So if you want to do parallel communication, you may have to use entire port 1, all 8 pins at a time, or 16 pins while combining ports. So that's a drawback. So it is faster, parallel communication is faster, but serial communication takes less number of pins. So that is one of the key advantages of serial communication, and disadvantage is slow speed. Now there are different types of serial communication, like synchronous and asynchronous. So I'm giving you the introduction. So rather than straightway jumping into the code, you have to understand what is the basis, what is the theory behind, and what is the reason, what are the reasons. So there are different types of serial communication, such as synchronous and asynchronous. So synchronous means serial communication which is having a clock signal, which is absent in UART. If you see this, there is no clock as such. So the signals are all digital here, TX and RX, but there is no dedicated clock line. So UART comes under asynchronous. So that's why it is called universal asynchronous receiver and transmitter. So it's an asynchronous mode where no clock signal is used. But why? What is the advantage of putting a clock? Clock actually increases reliability at higher speed of serial communication, because serial communication can go up to several gigabits per second today. even terabits per second in some of the modern technologies. So there, it is preferred to have a clock. Otherwise, sometimes if there is little timing mismatch in asynchronous serial communication, you will lose data possibly. So that's why, but asynchronous is very nice if you work until few megahertz speed of communication, whereas synchronous is typically used from any low speed to extreme high speed, whatever the maximum ones available. Now, there is something called baud rate in serial communication. So baud rate is nothing but bit rate or bit transfer rate. It's the speed of serial communication. So baud rate is essentially the speed of serial communication. That means how many number of bits per unit time, that is second, how many bits per second. So let's say 9,600 bits per second, 1,15,000 bits per second, and so on. So there are some standard serial communication rates which are applicable to UART, but as such, baud rate is in general, it's the speed of serial communication. Now, there is something called data framing. In serial communication such as UART, we arrange the data in a particular manner, in a form. That means we just decorate or arrange the data before sending from one side to other side, like device 1 to device 2. So we need to do some sort of data framing. That means we have to arrange the data in a particular format, and then you send the data. So that is called data framing. Another complex, or rather another concept, not complex, another concept is about half duplex and full duplex serial communication. Half duplex means, so you can only do one of these two communication paths active at a time. So any one of these two red lines should be active. That means we'll take data at a time. So that is half duplex. Duplex means bidirectional, half means one at a time. Okay. So that is half duplex, and full duplex means, as you can estimate, so both the red lines will be active. So while the first device is transmitting something, it is also able to receive something, some other data. So that is full duplex. So it's a bidirectional, but simultaneously data transfer is happening. And obviously, there are several pros and cons of UART as compared to other serial communication that we can look at this last question later on as we go along after 8051. So as I said, if you look at this UART data framing, so let's start from here. We'll go around baud rate also, and we will actually then go to the program. So these 2 points are very important, data framing and baud rate. These are some of the characteristics or properties that we should look at. Now, serial data transmission can happen with certain data framing. So as I said, data framing is the arrangement of bits or arrangement of data information such that you can have a particular format such that the other guy can receive. So one device 1 is sending something, device 2 should be able to recognize which bit is what. So what is the meaning of every bit? So that is called framing. And here we use 8-in-1 UART frame example. So there are different frame examples available for UART. 8-in-1 means, you can see 8-in-1 means 8-bit data. So data width is 8-bit. So there could be 7-bit or 9-bit or 10-bit data also available. Actually, typically 7, 8, and 9 are the 3 options here. Then no parity, so that means you are not sending any parity information of the bits, about the bits. So you're just sending the raw bits, and then one stop bit. So stop bit is something, there are some start and stop bits available in UART communication as a part of framing. Now, the framing framing may include framing pattern may include 1 or 2 stop bits. Okay, so there are 2 options here. So 1 or 2 stop bits. I'll tell you the meaning of the thing. But must be only one start bit. So that is a compulsory thing. One start bit is compulsory, but 1 or 2 stop bits may be present, and that must be known to the other guy. Basically, device 2 should also be knowing that what is the frame sequence for a given data transfer. Now, if you look at this, so there is a start bit information. So this is some time. So x-axis is time here, and y-axis is logic level. So this is logic 0, this is logic 1. And this is time t equal to 0 and onwards, basically with certain unit time instances. Unit time instance means this is the bit time instance. So each arrow each double-headed arrow indicates 1 bit time. Okay, and this time may be in microsecond or millisecond. If you take a reciprocal of this, so that will give you the baud rate. Okay, so there is some finite amount of time here for every bit, and whatever time is there for one bit, it is throughout for all other bits. So that means all these arrows are representing same time duration, just one after another. And there are 10 such arrows. So that means there are 8 bits data, but there are total 10 bits in a given frame, including start and stop bit. So start bit takes 1 bit time, stop takes another 1 bit time because 8 in one format, and then additional 8 bits are there in between. And while the 8 bits are packaged, D0, which is the least significant bit, and D7, which is the most significant bit. So look at the arrangement. So least significant bit comes immediately after start, and most significant bit comes just at the last before the stop signal. Now look at this for D0, D1. So it's like a box, rectangular boxes arranged in this timing waveform. Whereas for start, it is only the upper side of the box is missing. Just a moment. And the lower side of the stop is sorry.
It is stuck on the first slide, device 1 and device 2. I don't know what you're talking about. Like, I can't see the start, and yeah, now it is changing, right? Yeah.
Oh, that is strange.
Now it is back to 1. So like, now it's a device 1 and device 2. Yeah, now it's correct. Yeah.
Actually, IIT. Okay, can you see my screen?
Yes.
Yes. Which slide you are looking at right now?
8 and 1 UA RT frame, right?
Okay, I'm not sure. Today in the morning, I was facing internet issues. Anyways, we'll continue. So here, so you can see a UART data frame where there are 10 arrows shown over here. So each arrow represents 1 bit time, and all these arrows are equal in time width. So that means if you take the time width or time duration for one of the arrow, so it is same for all others, and the reciprocal of this time for one arrow is called as baud rate. So as you can see, what is a baud rate? So baud rate is just a reciprocal of this particular time duration. So this time may be in micro or millisecond. And in this particular frame, you can see there are 8 bits D0 to D7 packaged with start and stop bits. Okay, and now start bit is nothing but a active or rather low duration for one such arrow time. Okay, so start bit is just 1 bit duration where the signal is logic 0, and for remaining D0, which is the least significant bit, comes first, and D1 and so on up to D7. So we can have either 0 or 1 for each and every bit, like each D0 may be 0 or 1, but any one at a time. Same thing for all other bits, and until D7 that happens, and then at the end of a frame, so the stop bit comes. That means the logic level of the pin should be logic 1. So suppose if I want to send in the previous slide, so let's say I want to send some data, 8-bit data from TX of device 1 to RX of device 2, and the value of the data is, let's say, FF. Okay, so FF is a hexadecimal number which can be represented by all ones. All 8 bits are all the 8 bits are 1. So if I want to send hex FF data, so I'll first, how do I arrange this frame? I'll first make the start bit to be 0 because it must be 0. So that indicates the other guy, receiver guy, that I'm starting something after some idle time. Okay, so this idle time rate portion should be some duration of time which is preferably more than the bit time. Okay, so you give this logic 0, so then the receiver gets to know the transmit is sending this signal actually, then receiver is accepting the same signal, reading the same signal. So after logic 0 for some bit duration, Then the D0 bit will come. Now I want to send FF, so that means 1 1 1 1 1 1 1 1. Okay, so FF means I have to start from the MS bit side. So all bits are 1. So after this logic 0 time, so then it will remain 1 for all 8-bit duration. Then for the 9th bit also, or 10th bit in this case, from this particular starting age, so the 10th bit will also continue to be logic 1. So if you look at this data on oscilloscope, you will find this little pulse, negative going pulse for the start, and remaining all bits are 1. So that is how a data frame for FF will look like. If it is 0 0, you can just substitute everything on these bits. So it will be, so one starting age, this 1 to 0 age, and then it will 0, and then again it will continue for 0 all over, and just one upgoing pulse like stop pulse will be visible on oscilloscope if you would like to look at it. So in UART it is always mandatory, rather it is mandatory to put LS bit. So this is, if you write a small letter B, that means bit. If it is capital letter, that is byte actually. So in this case, we are talking about least significant bit first. So that's the frame sequence. Now let's look at some more technical issues with UART, how it is happening. So you know by now, so how the connections are made, how the data looks like, and what is the meaning of bit duration or the baud rate. Okay, so baud rate is the reciprocal of the bit duration, which is implied through this double arrows. Now, having said that, we will now go to more basically deeper stage where we'll target the programming part, how to use the microcontroller for this serial communication. For that to happen, you have to understand some more hardware part and some little simple calculations. So here you can see the oscillator is there, crystal oscillator for time-based or clock generation is there for any microcontroller, and the oscillator signal is given to some sort of divider. So this diagram on the upper side is only for 8051 microcontroller. So different microcontrollers will have similar diagrams where these numbers and the shape of this diagram will change, but it is very basic and it is for 8051 only. So the oscillator frequency gets divided by 12. Basically, it's like divide by 12 kind of clock. Basically, it's like a counter signal where it takes 12 pulses and then it increments or decrements by 1. So typically it gives 1 pulse after it takes 12 pulses. So that is the meaning of this frequency divider. Now, divide by 12 clock is called as machine cycle clock. Okay, so machine cycle clock is something like how many, what exactly the hardware inside the microcontroller is saying. Now the question is why it is required to divide it some number, why it is not divided by 1, or why it is not directly connected to the machine cycle clock. It would have been faster. The problem here is that, so this clock is basically having so all the peripherals of the microcontroller may not be as fast as the processor itself. So from there, this concept came, although in today's technology that this definition is still valid, but not everywhere. But during 1970s or 80s, this was extremely important, that to consider your peripherals are not as fast as your microcontroller, ALU, or some special part of the microcontroller like instruction decoder and so on. So the peripherals used to be very slow or comparatively slow as compared to the main microcontroller or the timing and control unit. So some key areas of the microcontroller. So to match up with the frequencies, so it is necessary that it is divided by some value. So that is one of the reasons. So there are other reasons actually I can discuss why it is divided, but let's not digress. So we divide it such that we can use this clock for the peripherals, and here the peripheral is my either serial communication block or timer block or other input-output blocks. Now, so why input-output blocks are slower? One reason is that the higher pin capacitance or higher capacitance, that means that increases time constant, and as a result your speed reduces as compared to the main microcontroller, and that's why you need some reduced clock, and we call that as a machine cycle clock. That's a name which is used which is used as a primary clock source for the peripherals. Now we will use, so for having this timing information like every bit timing, so there are different ways to do that. You can use simple delays like DJNZ kind of delay that we discussed earlier. So this kind of delays like wait 3 that we have DJNZ some register. So this method is not very effective, as I said earlier. So instead we can use timer to generate that bit duration for the UART or serial communication. So for that to happen, we have to further divide it because UART standard speed is significantly low as compared to those megahertz value for the crystal. Okay, so typically it is up to several lakh bits per second, whereas this is several million bits per second, right? This clock is in megahertz and this is in kilohertz. So the UART typically works in kilohertz, as you can see later on. So we have to further divide the clock frequency by some amount, and that is 32 in this case, because whatever timer clock is there, so it is not directly receiving the crystal clock. So whenever you use the timer, it actually gets divided by 12 and then it further divides by 32 and then it comes to the timer. So that will lots of reduced frequency actually clock is applied to the timer. So that's one reason. And so once you have the timer clock, you can keep on generating this bit duration for each and every bit, given some hardware is there inside microcontroller to make sure that all these bits are automatically framed and it actually gets passed on to the other microcontroller through TX line or coming in from the RX line. Now, how do we calculate this baud rate? So based on this block diagram, so we can have a very simple calculation for the baud rate. So let's look at the acronyms first. So the frequency of crystal is F extal, and then the machine cycle clock, which is there, which is divided by 2, F crystal divided by 2, divided by 12, which is M clock, and then timer clock, which is further divided by 32, as you can see here. Then BR is the baud rate or the bits per second. It's the speed of communication, as I said. And TH and TL are the registers in the timer. So you can use either both or any one of them. So in this case, we are using only one of them, which is the 8-bit timer mode. So that's why we are considering TH. So we can also use TL, but there are restrictions. So it's in 8-bit mode, TH is actually preferred as per design of the internal design of 8051. So that's why TH is considered in 8-bit mode. So we are going to use 8-bit mode. So you can see the simple calculations that I just mentioned. And so how do you find out? So given a baud rate, so given a bits per second, so this is baud rate is bits per second. So this speed of communication is known. So given you choose any one of the standard baud rates. So in UART, there are standard baud rates. So this is just 4 examples, but there are a lot more on the higher side and few more on the lower side than this one. Okay, so assuming we just consider this any one of these 4 standard baud rates, so we cannot use 9620 or we cannot use 9500 kind of baud rate in UART because of the standard set by the companies since 1970s or 60s even. So UART was originally developed by Hewlett Packard, HP, guys who make printers. So HP actually originally developed this UART protocol, and that time it was not called as UART, it was called as serial communication protocol, simple serial, because there was no other competitor available with UART. This was one of the very first serial communication protocols. So they developed certain fixed bit rates, and that's what we are still following even today. In most modern microcontrollers also follow those standard baud rates. Obviously, there are higher limits available, which has been expanded, but those rates are still available. So now there are some coefficients. So based on the calculation of the value of TH1 for serial communication, we should use this particular equation, which is 256 minus F crystal divided by 384. 384 comes from multiplication of 12 and 32 divided by baud, which is the number of bits per second. Okay, so you can actually find the value of TH1 that you should be storing given you know the crystal frequency and you know the baud rate. So these are the two variables which must be known. And crystal frequency is fixed for a given microcontroller once you choose a crystal oscillator. And Baud it is your choice, obviously. Based on that, you have to set the value here. So assuming 11.0592 is my crystal frequency, and this frequency is actually very commonly used for standard Baud rates. So this is a specially cut crystal oscillator which gives a resonant frequency at 11.0592. So resonance part is, so that those are analogous manufacturing part of crystal. So let's ignore this. This is one of the standard easily available values. Assuming this value is used, you can actually put different numbers which comes over here. So this minus basically represents, it's not a real minus number. It is just indicating whether your most significant bit, which is D7 of TH1, is 1 or 0. So there actually you get the minus sign over here in decimal representation. But actually you have to store to some binary number, right, in this 8 bits. So that binary number is further represented with hexadecimal here. So you have to, if you use 11.0592 megahertz, and if you want to do your communication at 9600 bits per second, that is 9.6 kilobits per second, you have to use this FD as the coefficient in the TH1 while running the timer for UART. Okay, so that's the meaning of this particular table. Now we have to look at some more details of the hardware part of the microcontroller. We skipped some of this earlier because I don't want you to remember again. You can always refer to the datasheet and understand what is the meaning inside all these bits. So you don't have to remember the exact pattern, but you have to preferably remember the name of the SFR and their functions. That's all. But later on, you have to understand and remember the purpose of this, and that you can find in the datasheet or manual. So these are the three registers that we need for serial communication. First is serial control register, SCON, then timer mode register, and then power control register, PCON. So this we had explored T-mode to some extent earlier, but SCON and PCON are new ones. So let's look at our other slide where I was showing you the 8051 registers. So I think this is quite familiar with you right now, SFR organization. Then we need SCON. Okay, SCON. So SCON has 8 bits. So this is from the hardware manual. I've just copied to the slide. You can see different bits. You have to understand what are those bits. So let's look at from this 0th bit, and then we'll come up to the 7th bit. Okay, so D0 in SCON is receive interrupt flag. So and D1 is the transmit interrupt flag. Now these flags can be used along with real interrupt, or it can be used just for polling purpose. So that means whether receiving is completed or not, so this will become 1. Whether transmission is completed or not, it will become, this TI bit will become 1. Okay. Now, for certain operations, we need, you have seen 8 in 1, so there could be 9 in 1 also available. Okay, so for that, so this R8 and T8, TB, RB8 and TB8 is basically representing transmit bit 8 or receive bit 8. Yes.
So I think have you shared another document because we can only see the previous slides.
Oh, today, okay, I understand your problem. Yes, I'm sharing the other document. I'm using the MS Teams app, but it is misbehaving somehow. Okay, just give me a moment. You are saying this important registers to configure only?
Yes, sir.
Okay. Just a moment, I'm trying to. Okay, can you see my screen now? What you're saying?
I see 31006 folder.
Okay, and what are you seeing now?
Yeah, now this is
It's
some
gone.
different slide. It's gone. Yeah.
Okay, okay, I was referring to this one. Okay, let's continue. So I'm talking about this ISCON register, which is an 8-bit register present inside the SFR, right? It's one of the special function registers for serial communication called as serial control register, ISCON. So there are 8 bits, as you can see. So I'm actually talking about D0 onwards towards D7. So I went to this slide where I was talking about. Uh, so SCON has several bits, all those 8 bits, as I said, and the D0 bit of SCON is a receive interrupt flag. So that means if the receiving operation is completed, so let's say we have enabled the UART, and afterwards if we do some reception of data and reception is done, so that means this bit will be set. Okay, so after the stop bit is received, so that is set by hardware at the end of 8-bit in mode 0, and there are other modes also, so that we can see. And if reception is complete, if the microcontroller is receiving something and all 10 bits are done, in that case this flag will be logic 1, and if you read this, it will be clear to 0. Same thing for the transmit TI bit, which is D1 bit. So transmit interrupt flag, if you want to transmit 8-bit data, so that means it will become 10 bits after framing. And once all those 10 bits are gone outside the microcontroller one by one, then this bit will be logic 1. So this is called transmit interrupt flag. That means it will indicate whether your transmission has completed or not. Then we had seen 8N1 format, right? In the framing, I discussed 8N1, that means 8 bits, no parity, and 1 stop bit. Suppose if we use 9-bit configuration. So instead of 8 bits, so data is D8 to D0. So that means there are total 9 bits. So where to keep that 9th bit? So for transmit and receive, there are separate bits available in ISCON, where we can keep that 9th bit. So suppose something is coming, 9 bit is coming from outside, RB8 will be storing that 9th bit, and remaining 8 bit goes to some other register that I'll discuss. And TB is for transmit. You want to transmit 9th bit, so every register can take only 8 bits. So 9th bit is actually kept, that is D8 bit is kept at TB8 over here. Now, more importantly, so there is a reception enable. So suppose if you want to enable your UART, so now there are different bits here in ISCON itself, where you can enable, disable certain functions or set the different modes, as you can see. So REN is the reception enable bit. So it's a bit that will enable the data pin, or basically RX pin or RXD pin, to receive data. So it's basically a on-off switch for whether you want to receive any data from outside world or not. So REN is set to enable serial reception and reset to disable the serial reception. Now, let's not look at this moment. We'll jump to this SM0 and 1 bits actually. So this is more important. Then we'll come to D5 bit. So the mode selection is very important in UART. So first of all, you have to say that whether you want to, how do you want to use the UART? So what is the mode of operation for UART? So you can use it 8N1, that the example which is very commonly used mode of operation, which is 8-bit UART mode, and you can select any baud rate of choice which are actually available from that list that I showed, the standard list of baud rates. And if you want to invoke this particular 8-bit UART, this is called as mode 1. And this mode 1 is set by SM0 and SM1 bits, which are present in the ISCON register. So if you consider SM0 as D7 and SM1 as D6, in that case, if you select this at 01, then 8-bit UART mode is invoked. And for that 9th bit operation, that means that TB and RB8 bits. So you have to enable this mode 2 of the UART, which is a 9-bit UART mode. Okay, and where the baud rate selection is either divided by 32 or 16, that we can see how it is done. So typically we don't use other three modes. So we just use 8-bit mode, which is almost 100%, very close to 100% cases you will use this mode. But there are instances where we need this 39-bit UART mode, which is extremely rare. Actually, I have never seen any example or any communication in real life where it uses 39 bits. But originally this was decided to make so many number of start and stop bit. If you want to transmit a large sequence of data bits, then why to use many start and stop bits? So that is going to add some extra time, right? Every time you send 8-bit data, so 2 more bits are coming as a penalty or overhead. So let's reduce the overhead and use a longer data frame. So using 39-bit data frame. So, but again, it is error prone. So because less number of sync is happening because of absence of start and stop bits. So this is almost not used. 9-bit is still in use in certain cases. 8-bit is almost 99.99% cases, I'll say. And shift register mode, it is again very rarely used in 8051 or any microcontroller side, where it is like a parallel input serial output shift register, and other way around, serial input parallel output shift register. So this is mode 0, so which is again very rarely used, but you can shift some data without start and stop bits. Basically in shift register, start and stop bit are eliminated, and simply you are sending 8-bit or 9-bit data, just one after another, or even longer data. Depends how you are managing your data inside. So there is no framing bits like start and stop bits. So as a result, shift register mode is also error prone because it can get desynced to where is your D8 or where is your D7 bit. So that exact location of MS bit or LS bit is may get out of control if you have slight error in the program code. Whereas in 8-bit and 9-bit mode, even 39-bit mode, you have all start and stop bits in this mode. So it is relatively less error prone, but again 8-bit is the most commonly used. Now in multiprocessor mode, so there is something called multiprocessor mode, which is mode in serial port mode 2, 39-bit. So this multiprocessor mode, basically any UART is first of all multiprocessor. I am telling you, this is a misnomer. Why? Because if in UART you need 2 microcontrollers at least, right? So one transmitting microcontroller, one receiving microcontroller, or other way around. So you need 2 devices, 2 microcontroller devices. So by default UART is multi-communication or multiprocessor communication. But in addition, there are basically there could be daisy chaining application of microcontrollers. More than 2 microcontrollers or microprocessors can be used in UART communication. So that means it is basically, it's like a daisy chaining or some sort of network, star network, or typically tree network where more than 2 microcontrollers are used, and you can communicate between any 2 microcontrollers through a common UART or data line, serial data lines. So in that case, we use this multiprocessor communication mode where, so in this large frame of data, so some bits may be for some microcontroller 1, some other bits may be for microcontroller 2, and then the microcontroller will just keep silent while microcontroller 2 data is going, and other way around, microcontroller 2 will remain silent while microprocessor 1 data is coming into picture. So it is again error prone, as I said. So first and the last modes are quite error prone, but it is possible to make it error free through very careful coding and connections. Okay. So in serial port mode 2, so this multi-communication bit is actually set. So it's set to enable multiprocessor communication. So in mode 2 and 3, so again 9-bit can be used because if you have 3 microcontrollers, one is transmitting, 2 are receiving. In that case, the D8 pin can be used as an address for which of the other 2 microcontrollers. So this multiprocessor communication feature is there, where 9-bit can be used as address, or you can have more number of microcontrollers where more address bits serially transmitted address bits are available, and we can discuss this in later part because I'll first complete the serial UART, but this is actually very important and very simple also. Only thing is that apart from data, you have some address information along with your data within a given frame. That is the basic idea behind this more number of bits than 8. Okay. So, and then the last part is the framing error. So framing error is basically, suppose you miss a start bit or you miss a stop bit while starting a communication or while invoking a communication. So that is a framing error condition where the framing error is becomes a status bit. So instead of setting SM, it becomes a status actually. So SM is a control bit because we are setting the which mode, whereas framing error is a status bit, which is again multiplexed with the same location, D7 location. So framing is basically is cleared to reset the error state. So if there is error, you have to clear it up first. And if there is some missing stop bit or start bit, then it is called as framing problem or framing error, and then this bit will indicate. So microcontroller has to, the code has to read this bit in order to find out whether any framing error or not has come. Now the PCON register, so that is another register that I said that we'll be using in serial UART communication. So look at this, there are some bits associated. So PCON means power control special function register. Then PCON has basically 2 bits, D7 and D6, specifically meant for UART related thing. Communication. So this SMOD 1 is set to select double data rate in modes 1, 2 or 3. Modes 1, 2 and 3 means either on those UART mode, 8-bit, 9-bit and 39 bits. So these are and see this and in case and also there is a SMOD 0 which is actually set by the framing error bit in SCON register. So whenever it's cleared by select FM0 bit in the SCON. So this bit SMOD is actually related to the FE bit, D7 bit of the SCON register. Basically it is linkage that whenever FE is controlled, this is also set. So that means it is another status bit, which is an alternate status bit apart from the framing error. Because in the framing error, you can see that suppose I have it is multiplex, so I can set the SM0, but the framing error will be overwritten, right? If I write something to SM0, which is same location. So how do you know that FE is actually there was an error? So it is get updating in the SMOD 0 bit. So and if you look at the other register, other bits in the PCON, these are just turning off the power or just invoking different low power modes like power down mode or totally idle mode. So this each bit, if you set or reset based on that, there are different levels of power consumption. So such as power off means everything gets powered off. It's like a software power off. Okay, and power down is like a sleep mode. And idle mode is another type of sleep mode. It's basically some sort of hibernate mode actually. So hibernate is the idle mode where the processor will not execute any code unless you remove this idle state. And let's go to so and then T mod. We have seen T mod earlier, but we'll just quickly revise that. So in T mod, so we wanted to use timer in mode 0. So timer mode special function register. We want to use timer 0 in mode 2, which is 8-bit auto reload mode. See, after every bit time, so we should not be re-initializing the counter, which is there for other modes like mode 0 and 1. So instead, we want the next bit duration should automatically start once the first duration timing is elapsed. First bit duration timing is elapsed. So that's why we use mode 2. So we have to use this M10 and 00, and then we have to use basically turn on and turn off the timer 0 in our code. Okay, so these are the three, and now look at the values that I have written. So we'll use SCON equal to 50. So let's look at SCON equal to 50 means 0, 1, 0, 1 and 0, 0, 0, 0. So SM1, so SM0 and SM1, so this becomes 0, 1. that is 8-bit UART mode, right? So in SM0 is 0 and SM1 is 1. So that means this 8-bit UART mode is invoked, right? And then 0, 1, then 0, 1. REN is also 1. That means serial reception is enabled. Okay. So serial reception is enabled and multiprocessor mode is actually disabled. Okay. And now remaining bits are 0. That means 9-bit TB8, TB9 are all TB8 and RB8 are 0, and interrupts are also reset initially. So that means these are all 0, 0. So that is why I'm keeping it 50 0x50 to SCON. Now T mod equal to 20, that is another thing. So which are the 20 means your M1, okay, sorry, I was talking about timer 0, but we are using timer 1 here. So we can use timer 0 also. So there is no restriction as such, but we are using timer 1 in this example actually I have written. So M1 and M0 are 1, 0. So that means auto reload mode. So let's look at this T mod very quickly. Okay, 2 0, that means this M11 is 1 and M01 is 0. So 1 0, which is 1 0 for timer T1, which is mode 2, which is 8-bit auto reload mode for timer 1. Okay, and in auto reload mode, as I said, there is a hardware restriction, only TH1 should be used, and this is automatically reloaded with the original value of TH1 once you are actually getting overflow condition. So what it is done actually, so you have to upload the count value in TH, okay, and the counting is happening in TL, so in auto reload mode. That means this is just a storehouse, and once the counting is to TH gets copied into TL, and then counting starts in TL. Once TL becomes 0 after a certain time, then TL gets copied from TH. So TH is just keeping a copy of the data such that every time TL will be uploaded or updated with every time the overflow condition happens. That means every time the bit duration is elapsed, you will copy TH to TL and then start counting in TL. So that is the meaning of this particular configuration. In timer 1 we are using. Then PCON, we kept everything to be 0, so that means S mod, which is the D7 pin, which was important. So where is PCON? In PCON, so this is 0 basically, that means it is not set, it is clear, right? So that is not used in any one of this mode set to select the double baud rate. So what I'm doing, I'm using a normal baud rate. So double baud rate basically 9600 into 2 will be coming if you put that coefficient. So in double baud rate it's disabled. So S mod equal to 0, S mod 1 equal to 0, that means double baud rate is disabled. Okay, so that's what is given. So PCON is 0, 0. Now, given this register information, so we'll now start with the coding. So what we have done, we have first done the connection. We have understood how the data should look like. Based on that, we did some simple calculations and choice of parameters. And afterwards, we have determined what will go inside each of this special function register. And now it's the time to write the code. Now the code, the question that I framed for this code is that write an assembly program for 8051, and also later on I am using C example also for the same, to transmit an ASCII character M through the serial port. So let's say I can take any other character also, any special character also, but any one of the ASCII characters, because it is written inverted. You can use any other character. It's not restricted that you should only use ASCII. It can be any other 8-bit data also. So in this example, I have to send 8-bit value, ASCII value of M, capital M, through the serial UART at a particular baud rate, and I have to do this repeatedly while selecting a particular clock for the crystal. Okay, so that is my question statement. So I have to do this repeatedly, that is indefinitely it should keep on going. So what I've done, so I will starting with org 0. That means we will start at 0th location in the code memory space. Now starting the code, move T mod equal to 28. So I've remembered, I have to remember these values, whatever I've determined. So T mod 20, SCON 50 and PCON 0. So that's what I'm doing, T mod equal to 0. Now, you don't see any PCON initialization here because PCON is automatically reset to 0 by default after hardware reset. So we don't have to worry about PCON in this case, although we have to consider why we are doing PCON, why you considered PCON. But PCON is considered to be 0 automatically, but TMOD is initialized at 20. That means timer 1 in mode 2, which is 8-bit auto reload mode. Okay, with the byte should be updated on THX. Now, next instruction is move TH1 with the coefficient value. So from where I'm getting this -3, I'm getting from this table, right? I did this calculation earlier separately, and this is also available as chart for standard crystal frequencies. For 11.0592, it is FD, so or -3, anything, any one of this. So I can write move th1, 0xfd as well, which will again initialize to the same value to th1, which is an immediate addressing mode. Okay, so we have to see this is also immediate addressing mode. Now I'm doing SCON 50, so I've already initialized or determined SCON to be 50 in that mode, 8-bit UART mode that I wanted to enable along with receive enable signal. So that is why I'll just simply write 50 to SCON, move SCON comma #50 or 0x50. Then afterwards, I have to start the timer. So TR1 is a bit in the timer mod register. Okay, so where is TR1? So, sorry, TCON register. Yeah. So TR1 is the timer run control bit. Okay, so this is a bit in TCON register. So where if I set this bit TR1 equal to 1, then it will turn on the timer. Okay, so the timer will be started with this TR1 bit. So with this instruction set bit. So I'm starting the timer in whatever mode I already previously initialized. So make sure that you are turning on timer 1 while you are initializing timer 1 over here. Okay, and if you're turning on timer 0, obviously it will malfunction. So you have to keep track of this thing. Then there is a loop level where isbuff. So now isbuff is a serial buffer register. Now there is no format of this isbuff. It's very simple. It's just a blank special function register where the data for serial communication, either transmit or receive, will be residing. So serial buffer is nothing but a 8-bit simple register, a special function, but simple yet enough register, which will store the data for serial communication. Now what I'm doing, move isbuff comma #m. So my problem is that I have to send the character m, ASCII of the m character to serial transmit. So in 8051, so if you put after proper initialization, if you simply copy the value to isbuff, it will immediately start transferring the data. So that is the that's how 8051 functions. Okay, and that's how even other microcontrollers will also function. You'll see similar things. If you update some buffer register, then it will automatically start the transmission given you have initialized it properly earlier on. Okay, so we have already initialized serial communication in all those modes. 8N1, obviously no parity mode, where parity cannot be set in 8051. You can set the stop bit, you can set the 8-bit. If you look at SCON, parity control is not available. There are parity control is available in other microcontrollers, not in 8051, in the basic form. In advanced 8051, it is there. So after this instruction, so what is doing? We are transferring the ASCII of m to the UART port. So TX starts to send data. Okay, so transmit pin starts to send data over here. Now after this putting, you are just copying m to sbuff. So if inverted comma means ASCII of that character will be taken. The moment you copy M to SBUF, the data transmission will start, but it will not end. So there is no guarantee it will immediately end. Because as I said, data communication is happening at a slower speed, 9.6 kilohertz. Whereas your microcontroller is running at megahertz, whatever it might be, the 11.0592 in this case. So after 12 or 24 clock cycles, whatever this instruction is going to take, I think it will take only 12 clock cycles. So after 12 clock cycles, so that means less than 1 microsecond, it will come to the next instruction. Now we have to check whether the total, all the 10 bits have gone outside or not. So that's what we is doing over here by pulling TI bit. So TI is a transmit interrupt, if you remember, transmit interrupt in SCON register. TI is basically set by hardware at the end of 8 bit of time in mode 0 or at the beginning of stop bit of in the other modes. Okay, so the TI bit will be 1 if all your data bits are gone outside through TX line. So this JNB TI again, so that means it will wait over here, jump if not bit. TI again, so it will actually wait over here until the transmission is completed. All the bits from a data frame have gone outside. So once all the 10 bits are gone, then you will actually come to the next instruction. It will break the loop from the again thing, and then it will come to clear TI. So now that means you have already ensured that your transmission is completed. Then you have to clear TI. Otherwise, you cannot start the next transmission. Okay, the next time M you cannot transmit. So then you have to write this jump, in this case short jump loop. So the loop will basically again copy M to SBUF because SBUF is now empty after this clear TI or while this clear TI is coming. So SBUF is empty. So you have to reload SBUF with another character or same character or any other 8-bit data. So that's how it will again loop back and again it will wait until all 10 bits are gone. Again it will clear TI. Again it will do the same thing again and again indefinitely. So that's what is repeated task is executed. Now you must have read this code in C in the bottom side, where we have used C code, which is definitely much more easy to read as compared to assembly code, and you must have read this by now. So what I'm doing is I simply write tmod equal to 20. I can simply write, I can just move some instructions here and there, and then I will write pcon equal to 0 just for initialization purpose. Okay, I don't have to write 0x or something if it is 0. Then I can even put this on the same statement, same line, which is one and the same in C. But for flexibility, I'll just keep it separate. Th1 equal to FD, so which is -3 and so on. And you can write -3 also instead of 0x. Then you are starting the timer. Then open an indefinite loop, infinite loop with while one or for statement also equivalent loop can be opened. Then put SBUF and then wait for TI and TI equal to 0. So then basically clear TI instruction. So why I'm showing this both C and assembly together? What is the necessity? I am just trying to tell you what exactly the compiler is doing in the background. Okay. So based on your sequence of code that I'm writing in C, so whenever every instruction will invoke, so let's say this tmod equal to 20, it will invoke this move comma this number. Sorry. Whenever scon equal to something, it will actually put another move scon comma something just below tmod. Okay. So this is how the compiler will substitute each statement in your C with some statement or a group of lines in assembly. So then tr equal to 1, that means set b equal to tr1. Then while 1, so this is basically loop which gets started automatically with certain initialization. And then within that, it will automatically set the levels and then put the values for this whatever ASCII or binary characters binary values that you would like to put in the SBUF register, and while TI equal to 0, so that means GNB, this instruction is executed by this particular statement, and then TI equal to 0, that means it will invoke clear TI. So compiler essentially reads each and every part of your code, every line of your code from C, and it will substitute with necessary set of assembly instructions in the background. Okay, so that is what compilation is done. But here we are only transmitting characters M. We are not doing reception. So in the next code, we will do some receiving action. Okay, but here I am only showing C because I think you have now better understanding how C and assembly are interrelated. So we'll switch back and forth. So write a C program for 8051 to receive a character which is ASCII in format through serial port at a different baud, which is 4800 bits per second, that is 4.8 kilohertz, and repeatedly you have to do this reception and display the value. So once you receive 8-bit serial data, you have to display it or send it to port 2, which is a parallel IO port having 8 bits. So you are receiving 8-bit serial data through receive RxD line, and you will send 8-bit data in parallel form to the port 2. Okay, and this RxD TXD lines, remember, these are the real pins of microcontroller. Sometimes we call it RxTX, sometimes we call it RxD TXD. It's the same thing. Here, so we'll write again in hash include reg51. So see, reg51 essentially has the definition of all the SFRs, all the registers, all the instructions, and so on. So basically, reg51 keeps track, is the header file which keeps track of all SFRs. Suppose if you write some other SFR name which is not available in 51, so obviously it will not work. Okay, so it must be compatible, and reg51 works for all instructions in 8051. You start your main code, then so I'm defining a character, so my byte. So this character is nothing but a buffer location, 8-bit location, which will store my incoming data. Then initialize tmod equal to 20. th1 equal to fa. Now fa is coming from this one. So fa, I am asked to use the baud rate of 4800. So baud rate 4800 represents fa in th1. So that's why I am using this fa in th1. And then I'll start the SCON, because SCON, it will again invoke 8-bit UART mode with restriction enabled. Then I'll start the timer here. And so in the exam, I want you to write a comment for each and every line of the code. Okay, so if it is written exam and if it is MCQ, obviously it will be different in pattern. While 1, then you start the indefinite loop or infinite loop, and then you select and read RI. So you are actually waiting and reading RI to be 1. So if RI equal to 1, then keep on waiting over here. If RI equal to RI equal to 0, wait over here. If RI equal to 1, go to the next instruction or next line. So in the next line, what we are doing, so when RI equal to 1, that means it will breaking the while loop, indicates SBUF is filled up with some incoming data, 8-bit data. You have to remember this. SBUF was used for transmit earlier. Now SBUF is used for reception. So whatever data came from outside, it will keep on, it will be updated. Now, assuming you are not updating SBUF for any transmission operation by your own separately. In this code, at least I am not doing that. Okay, so assuming SBUF is empty and SBUF is filled up with received character, and then SBUF is getting copied to my variable, which is a character variable, my byte. Okay, and now once the my byte is getting updated, I am actually writing it or copying it, the 8-bit value to P2. So what I am doing, actually serial data came into SBUF and copying that value to P2. So it's not necessary that I must use this my byte. I can simply write P2 equal to SBUF. That is also possible. So that will save one line of code to make it one level of optimization, make it slightly better in timing. So so I can simply write P2 equal to SBUF after this while statement. Okay, so this is also possible. And then afterwards, I'm clearing receive interrupt flag such that I can start receiving another character. So that's why this is important. I have to make sure that receiving interrupt flag is 0. And afterwards, again, it will look back. It will again RI becomes 0 after this instruction. So RI will be again 0 for some time until the next time something comes and updates the SBUF. Okay, so that's how the receive and transmit programs are written in 8051 for very simple UART communication. Okay, so do you have any question at this point?
So,
Yeah.
it was mentioned that RI and TI would be cleared when we acknowledge, right? So, wouldn't acknowledge mean we just read its value itself?
Acknowledge, see, RI, okay, let's go to the definition. Okay, so clear to acknowledge interrupt. That means what? So it has to be cleared by your code. So that means if you're clearing this bits RI or TI, you are saying that I've already considered your status, I've read your status. Now I'm ready for the next level of operation or next set of operation. So I'm actually clearing it up. So that means it is ready to be set automatically by hardware. So that means the microcontroller's internal serial hardware is setting it, but clearing it is through the code. So it is our manual way or code way of acknowledging the microcontroller. Okay, I have read that there was some interrupt earlier. Okay, so that is the meaning over here. Clear to acknowledge interrupt. So that means there must be some interrupt. Now in serial communication, so here, so look at the name interrupt. So although we are doing polling over here, so now there is a caveat, possibly that's where the confusion came up. These flags are having multiple purposes in the sense that there are two ways to use these two flags, RITA. One is the polling method, because polling method means what? Means I'm actually using this while statement to read RI. So this is a polling method, or here actually JNBTI. So this kind of instruction. So this is I'm reading through the code what is there in TI. So and I'm waiting when TI or RI becomes one, logic one, uh, by the hardware itself, automatically by the microcontroller. Okay, so I'm waiting here. So this is, but while waiting, I'm reading it again and again, jump if not bit, jump if not bit, and again. I'm doing this just to make sure manual through manual polling method. So this is called a polling method for reading any data. There could be interrupt method for the same operation. So that means, so instead of looping in to this again thing, you can simply go and do some other work with the microcontroller. So that means it can execute any other code also. If you will activate the interrupt, I'll tell you in subsequent slides how to do that, how to use interrupt, and you can use same concept to replace this statement, this particular statement, with fully automated things, and you instead of this one you go and write and you execute other program, other instructions here instead of waiting, because it's a wastage of time, right? Until all the bits are going and it is going at a slow speed. So you're wasting the time of the microcontroller. So it's not necessary you have to always waste time over here. So this is not the best code that one can write. This is a polling method. Polling is good. It is simple enough, but it wastes time of the microcontroller. But look at the name of those bits, receive and transmit interrupt flag. So it can be linked with the automated polling thing. Like whenever this bit becomes one, there will be interrupt service routine which will be called. So that is a possibility also, and that is absolutely possible if you enable interrupts through the interrupt registers that we will see separately. Okay, so this interrupt mode, so this reading is also happening automatically, and once you enter the interrupt service routine, you have to again use this clear, basically manually you have to clear by using the instruction clear bit kind of thing, CLR, TI or RI instruction inside the interrupt service routine. So this instruction will again be there in interrupt mode. Only advantage is that you don't need this kind of wastage of time in this loop. Okay, so for both transmit and receive, you can actually do this. You don't need this. If you use interrupt for serial receive and serial transmit. But obviously, you have to use this kind of instruction. Okay. Okay. So let's look at the interrupt side now actually. So we'll take again very few examples and very simple examples, but very relevant and useful that you can use it for complex operations. So these concepts that we are using here are actually quite generic in nature. That means all, as I said, ARM or any other modern microcontrollers use these basic concepts. The code also looks pretty much similar, only the name of the registers will change in ARM, or the way that we access the bits and bytes, so they'll be changed. So instead of character variable, we'll be using integer variable for 32 bits or 16-bit numbers. So those things are going to change in ARM-like processors. But whereas this while kind of statement, for instead of RI, there'll be some other bit for receive or transmit. So here, instead of 8-bit serial buffer, there could be 16-bit serial buffer and so on with different names. So those minor changes will come up with ARM. But otherwise, the code will look pretty much similar. Obviously, ARM is more powerful because of its internal architecture, the technology of the hardware that it uses, and some concepts, obviously like pipelining and so on, and different signal processing capabilities. But essentially, the code and the basics are, we'll say, more than 70 or 80% same as 8051. With definitely there are differences, minor differences. So let's look at an interrupt. Again, the interrupt structure that we'll be learning here is again pretty similar to hardware interrupts in ARM and other processors. So there I can speed up because here we are clearing the basics. Okay, so let's look at the question first. Write an assembly program to interface pull-down switches to INT 0 bar and INT 1. Sorry, I made it to INT 0 and INT 1 bar switches. Okay. While the first switch INT 0 displays AA through port 1 for a certain time, and then if you press the other switch connected to INT bar, it will show FF to port 2. So this is basically just a simple problem statement I was trying to frame, and similar examples are there in the book also. So I'm just trying to use the hardware interrupt in this case. So INT 0 bar and INT 1 bar are the two pins available in the microcontroller 8051. So like TXT, RXT, as we had seen earlier. So if you look at this diagram, so there are some RXT, TXT. So whenever in the previous example, TXT, RXT was representing 3.0 and 3.1, whereas here in this example, INT 0 bar and INT 1 bar are representing 3.2 and 3.3 respectively. Okay, so assuming these two pins are connected with some external switches from the at the external side. So this is how the pull down switches are connected. So it's saying, I'm saying that interface pull down switches. So pull down switches are like this between ground and INT bar, any one of those INT pin, and then there's a pull up resistor. About 10K or slightly larger resistor can be used. Even 4.7K onwards you can use very safely. And then this is a pull-up resistor which is connected to the VCC supply, and this VCC may be 3.3 or 1.8, depends on your technology for the microcontroller that you are using. In this example, 5, because traditional 8051. Now this tapping center, basically this middle terminal is connected to those port 3.1 or 2, depends on which INT. And there are different INT interrupt sources that are entertained by the microcontroller 8051. You can see in this list that there's a reset interrupt source. There could be INT 0 and INT 1 interrupt source, which are hardware interrupts. Then there could be timer interrupts for timer 0 and 1 separately, and also serial UART interrupts separately. So these are the possible interrupt sources which are used in 8051. Let me drink some water.
Okay. And look at the other column on this interrupt table. So this is called an interrupt vector table. So interrupt vector table is nothing but a table which shows the vector location for various interrupts. Okay, so interrupt vector table just shows shows the various memory locations in the code memory space, basically. So it actually represents code memory space. Okay, so this interrupt vector tables are again present for each and every microcontroller that will come across. So it means that every interrupt, if it gets generated, it goes to the program counter is going to certain memory location. So it is basically code memory space or program counter. The program counter values after every interrupt possibilities. So the program counter are, I'll just write in short, PC values actually, PC update values. So the program counter gets updated with these values once this interrupts are coming. So that means if you put a hardware reset, like we had seen with the CR combination hardware connection, at power up there is a hardware reset that automatically comes, which makes the program counter to go at 0000. Okay, so that is by default. So that ORG 0000 was redundant actually, to be very frank. So, but if you really put the hardware reset, it will come to 0. But if you put INT 0, it will come to some other location which is very close by actually. So 0003. Same similarly for timer 0, another location, timer INT 1, another location, and so on. So this all these interrupt sources are having dedicated values which will be simply copied into program counter. So this means that interrupt vector address is automatically copied to PC program counter, and program counter is always pointing it to the program memory or code memory. So program counter gets automatically updated whenever this interrupt comes. Okay, so if you obviously have to turn on every interrupt except reset. So reset is by default always on. So this is always on. Okay. In technically it is called non-maskable interrupt. So that is also another way of representing always on thing. Non-maskable interrupt. This non-maskable interrupt is only reset, not others. You have to remember this. Reset means non-maskable means you cannot stop this interrupt. It is having highest priority. It is always on. So that kind of interrupt actually. Highest priority at the same time always on kind of interrupt. So so this is reset is you don't have to enable it separately. But other five variants should be initialized. It should be either enabled or disabled. Okay, so others are called as maskable interrupt. Other categories are other five are maskable interrupts, basically all five after this reset. So maskable interrupt means I can turn off. So it is not always on. It is on only when I need it. Okay, and look at this. If I write, so if you go to this program kind of thing, org00, and then you are writing a bunch of code over here. So after I think after the second or third line, so you are likely to override this 03 location, right? So after second instruction itself, you are going to override this. So you have to make sure in interrupt routine, if you are enabling any one of these interrupt maskable ones, then you have to make sure that it should not override or overlap with these particular locations. Okay, 0B, 03, and so on. So we'll see how it is done. And interrupt, we also have to look at this register, IE register and IP register. There are two important registers. So let's look at the format of IE register before invoking or writing the code for this question. So EA is basically disables all interrupts. So that's when it disables all maskable interrupts. Okay, all means not reset. Reset cannot be disabled. You have to remember this, disables all maskable interrupts. And EF equals 0, no interrupt acknowledged. If EA equal to 1, each interrupt source is individually enabled or disabled. That means if EA is a master control for all the maskable interrupts. So if EA equal to 1, then you can individually turn on or off this maskable variety. Then if EA is 1, then only the other bits are useful, like timer 2 interrupt enable. So timer 2 is not present in 8051, it is present in 8052. Okay, in 8051 only timer 0 and 1 are present. Obviously we should look at these bits. So timer interrupt enable bit and external interrupt enable bit and so on. So this external interrupt means INT 0 and 1. So external interrupt 0 or external interrupt 0 means INT 0 bar, external interrupt 1 means INT 1 bar. Okay, so this bits can be enabled or disabled only if EA bit is 1. If EA is 0, that means all maskable interrupts are of no use. And by default EA is actually 0. Now let's read the problem again. So I have to put two switches to this interrupts pins, which is connected obviously, and then I have to transfer data to port 1 with AA if switch with INT 0 is pressed, and 55 if to port 2 if INT 1 is pressed, switch with INT 1 is pressed. Now, at this point, I would like to make a disclaimer. Some of you must have studied ARM and AVR at your leisure or as a hobby for other projects. Now, you will find one difference over here with the 8051 and those AVR or even MSP430 PIC or even ARM. So the difference here is that in 8051, we do not use a separate register for configuring the direction and purpose of 8051 pin. For what I'm saying is the following, I'll repeat it. Suppose I want to use this TXD, RXD or INT 01 or any one of this T0, T1, so on. I don't have a separate register in 8051 to make the direction set, whether it is input or output, whether RXD pin or 3.0 pin, whether INT 0 bar pin or 3.2 pin. So alternate function or IO function, as well as the direction of each and every pin within this alternate or IO functions are done just straight away without any extra register. So in AVR, ARM, MSP, PIC and other processors, you will find extra registers where you have to first determine which of these modes, which input or output or alternate or GPIO mode, general purpose input output mode. So which is absent. Why it is absent? Because of the following. Because of this port circuitry. So because of the hardware connections with every port and obviously the architecture which is linked to this circuitry. So if you look at all these ports, look at this input side. So from any pin, this is the physical pin, this rectangular box. From every pin, there is a direct buffer connected for the read. Only thing is that there must be some read control, which is automatically done by timing and control. Okay. So, and now it is coming through the internal bus. So that means if this read is actually going feedback to this D flip-flop also actually. Okay. It is true for every port pin. Whereas for more modern microcontrollers, there is a multiplexer. So this kind of multiplexer is used along with the pins over here at this point, where you are taking it to this rest of the circuitry or the alternate circuitry of the IO ports. Okay. Or even by setting the multiplexer, so this is not just 2:1 multiplexer, which may be more than 1:something something X multiplexer, where it determines the input direction, output direction, alternate functions. Even there could be multiple alternate functions for every pin, more than one. In 8051 only RXD / some P3 point something. Okay, but there could be in modern microcontroller there could be 5, 6 alternate functions for every pin along with GPIO. So that means 7, 8 functions are possible with every pin any one can be used at a time. So for that, there is a multiplexer which is used in modern microcontrollers, which is absent over here, 8051. So the advantage is that you don't need a special register to configure those multiplexer. So as a result, your coding becomes slightly simpler in 8051, which is just one step or one or few steps more in other microcontrollers. You have to set those pins. Now coming back to our problem statement, so assuming there is direct connection to this INT 0 and 1, and one more small thing I ignored. Look at this, another thing for all these port pins, there is a pull-up resistor, but this is a pull-up network, or this is just a resistor about 10K or so on. Okay, so such resistors are internally present. Even in this case also, this upper transistor acts like a resistor if this AND gate is enabling the upper transistor. Okay, in port 0 mode, which is possible. You can turn on through this while it automatically happens while address data thing comes. But otherwise, this upper transistor remains visible in port 0. But in port 1, 2, 3, this resistor, pull-up resistor is always present. Okay, so this resistor is always present, and that means, so in our program, for interfacing switches, this resistor is optional. This resistor R1, R2 actually is not required unless you are changing this to port 0 pin. Okay, if you put it in port 0, then these two resistors are mandatory. Okay, remember this fine observation. So since it is connected to port 3, INT 01 is multiplexed with port 3, and port 3 is having that pull-up resistor, so you don't need actually this resistor. If you put this resistor, there is no harm. This resistor comes in parallel to the internal resistor. So there will be some extra current flow while you press the switch. Okay, because two resistors, internal one and the external one, comes in parallel, effective value reduces. Okay, so having said that, let's look at the code. This is an interrupt code, and as I said, you must avoid this vulnerable locations which may be overwritten with the code. Okay, so that's why I originated at 0 after reset, because after reset it will automatically come to 0, and again redundant, just for safety we are putting it. I'm putting long jump to start. Okay, although long jump is not required, the code is not so long. It is not more than 128 bytes. If it is more than 128 bytes, L jump will be required. Okay, but here long jump just for safety purpose I've given. So you can use otherwise S jump or A jump over here. So long jump to start. So start is located at a very far off position, which is org 0040. Okay, so this org 0040 I have chosen such that it is far off from any one of the serial vectors. Okay, far off even from this inter-vector addresses. So that's why, so I've just started the program and just jumped to my main code, which is far off, starting at 40H. Then I've started doing this move IE, 85. Okay, so interrupt enable register with immediate addressing data, I'm putting it 85. So what is the meaning of this 85? Look at this. IE register is 85, right? So IE 85 means 1000. Okay, so that means EA equal to 1. So that means I can individually enable, disable this maskable ones, interrupts. So what I need, INT 0, bar and 1 to be enabled. So I need to put logic 1 to this bit EX0, which is D0, and I need to put logic 1 to this EX1, which is D2. Okay, so that way 0, 1, 0, 1 is coming. So there is 1, 0, 0, 0. Okay, so I'm enabling the global interrupts or maskable interrupts, and then keeping external 1 and external 0 bits 1, that means INT 0 bar and INT 1 bar are enabled as maskable interrupts. So that's what I've done over here, IE equal to 85. So that's how I'm getting this 85 value. Now, again, I am actually wasting time over here, you can say in principle. I'm just looping it indefinitely over here. It's like while one loop kind of thing. So where I'm looping indefinitely, so is jump loop, it will keep on doing the same thing until and unless some interrupt comes. So that means I'm ending the program. So this is again another assembler directive. So that means I don't have anything else afterwards. Although this is important because by chance if it comes after this is jump, so it should basically not malfunction. So is jump loop is invoked. So while this loop is going on, while one loop is going on over here, at any point of time, I can press the switches S1 or S2. Now, if I press S1, INT0 interrupt is enabled or coming from the external world. So that means program counter will get updated with 03. Alternately, if I press S2, INT1 will come and it will automatically change the program counter to 13. Now, what is the value of program counter here? It must be something higher than 40. Okay, because two instructions 40 and 41 are taken by this instruction, and then this is taken by 41, 42 and 43. Okay, so this 41 and 43 instruction, so that is the value of program counter while this loop is going on. So what I'm trying to do, I'm trying to think of hardware, what is going on in program counter while this instruction is going executed. So from here, logically, I can see that two bytes are used by this 4041 and then 4243 are used in the code memory space by this instruction. Now, the moment I press S1, for example, so INT0 will be invoked. So that means program counter will automatically change to this thing. And remember one thing with interrupt, the program counter, if the interrupt mode comes or interrupt signal comes, the program counter value, whatever 42 or 43 actually, so in this case 42 because it is looping over here. So 0042 was there in the program counter and that value gets updated in the stack. Okay, so whenever interrupt comes, then only it happens. The 42 value from the program counter is stored in the stack memory. And once the stack memory remembers that, then it will automatically call this program. Okay, let's say INT0 thing is done. So ORG00003 basically, which is the vectored location for INT0. So what I'm doing, AA. So my question was, I have to transfer AA to port 1 if INT0 thing comes. Okay, INT0 AA to port 1. So I'm actually doing the same thing. So initialize port 1 with 0xAA, which is immediate addressing mode. And then I can, I'm actually initializing a certain delay. So this is a simple ordinary delay where I'm putting some coefficient in R0 register and decrement in jump not 0 and loop with L1. So this indicates a simple delay routine for a blink operation. So that means I have pressed S1. So there will be a certain pattern of data goes into port 1 and assuming every bit is having some LED connected to it and the LEDs will blink, turn on for some while, and after some time the port 1 will become 0. So that means I'm actually forcing 0 into port 1. That means blinking will stop. This is just a one-time blink. Okay. So after that, it is returning from interrupt. So this is giving RETI. So through this RETI, what it will do? It will automatically apply two pop instructions because in this, due to interrupt, there were two push instructions for program counter, right? For 16-bit value from program counter were stored in stack. But with this RETI, there will be two pop instructions in the background, which will bring in the value 0042 into the program counter, which is the loop location. Okay, then again it will keep on looping over here indefinitely, and after some time, let's say I keep press S1. So S1, which is INT1 bar, which is S2. So INT1 is representing 0013. So I have to write another interrupt subroutine, which is shown over here, which is same duplicate copy of the other one, but with some minor changes. Here I want my interrupt 1 should do the blinking on port 2 with a 55 value. Okay, so that's what I'm doing. So updating port 2 with 55, then putting a delay,
simple delay, then resetting all the pins of port 2, after that blink, one time blink, and then go to return from the interrupt. So these two codes are pretty similar, and again it will keep on looping until another switch comes. So it's not necessary I have to press switch 1 and 2 in sequence. I can press 5 times S1, then 1 time S2, and I can make any random combination of pressing the switches, and based on that the blinking will happen. You can increase the delay, you can play out with the values. Instead of total port, you can put any one bit in the port, so you can play around with the values that you can use over here. Okay, so any question at this point?
Sir, why write the start loop stuff at 000, like at the 0th origin point?
It is because of this non-maskable interrupt, reset interrupt. Okay, so after reset or after power up, it is always going to 0. And why it is there? Because the main purpose is that it should be, your code should be deterministic. After you power up, your program counter can take any random value within that 16-bit range, that is 65,535 range. But we want a deterministic value in the program counter, because that is the main thing, looking at the code memory space, pointing the code memory or program memory. So after reset, it program counter automatically goes to 00, and I want that to happen because I can properly start my code from that point. Okay, so it is mandatory, and if in all microcontrollers you will find that, so in 8051 there is a slight difference with other microcontrollers, that this org something, so after reset ARM comes to different address, so it's not, this extra instruction is not required in ARM processor or MSP 430 processors. So you have to always write this extra instruction, right, after at org 00, which is sort of an extra thing that we are putting it. What if after reset it will come to any other location? In ARM and other microcontrollers, you will find that after reset it will come to some other location, not 00 location. Okay, so it is sort of a convention, post reset convention. So reset is a non-maskable. Is that clear?
Yes, sir. And so can you explain that calculation for 9600 baud rate? So why did we subtract it from like 256 minus the f of the clock divided by the...
Yeah, good observation. This one, right? So it is minus because it is down counting. So in auto reload mode, timer mode 0, mode 1, I guess, right? So this auto reload mode, timer in mode 2, in mode 2, which is a auto reload mode. So this, in this mode, so the value whatever you will be writing into TH is gets copying into TL register, and the TL starts down counting. Okay, so while down counting, so you have to minus it from the maximum value, that is 256, because maximum value is 256. So that means you will get only the remaining number of points that you can have within the 8-bit width. So that is why it is a minus thing in the equation. So this, it is different from this minus, obviously. Okay. So this 256 minus thing comes because of that, because it is down counting, it is not up counting. So overflow happens after it comes to 0 from a given initialized value. So that is why it is so. You can work out with certain values, and you can check this out. In every microcontroller, actually, it is minus only, actually, because most of them are having minus. Because in UART mode, there are certain timer in UART communication. So there are certain timer modes reserved for serial communication, and there it mostly does minus. But see, in ARM 7 or in ARM some other variants, you will find both up and down counting are available from the timer. But for serial, it is typically any one of these two, which is reserved particularly. So in 8051, it is only down counting, which is available in auto reload. So, and that is why, look at this actually. So -3, okay, so that is another way of looking at the same thing. So FD and -3 are same. So -3 from where? -3 from 256, okay. So which is FD, so which is the value in decimal, so 256 minus 3 is 252. So that 252 actually goes over there. So that's why the minus, basically this minus gets reflected in this form.
Okay, thank you, sir.
Yeah, good observation. So we'll go to our next topic quickly, and I'll release you by 10 o'clock. So please remind me if I'm over basically spending that time. So our next topic, I think I'll be able to start it and complete it by tomorrow, and that should be one of the last few examples. And this is very important example in terms of your understanding of embedded hardware development and system development. So obviously software is a part of it. So in LCD interface, so this LCD indicates a character LCD, which is a little oldish design. Again, I'm telling you with a disclaimer, because the oldish things are showing certain basics, which typically gets lost in more advanced LCD modules or more advanced interfacing things. So the concepts are absolutely intact, even with the most modern displays with touch screens and also multi-touch and all those things. Those are just additional things, additional sensors connected to your basic display device. So the basic display device, LCD liquid crystal display, is one of the basic devices that we typically interface with 8051. And the concepts are, I'll give you the relevance, how it is different than the modern touchscreen displays and other our phone displays with capacitive multi-touch things. As we go along, a little bit of tips I'll be giving you. So here I'm considering a traditional LCD display with 16 characters into 2 lines. So that is 16 cross 2 LCD. LCD stands for liquid crystal display. It is different than OLED display. So it is actually having different pixels where the contrast level or the reflectivity of every pixel is changed. Either it absorbs ambient light or reflects back. So that's how LCD works. So there is a there are pixels that you can see in these dots, and those pixels are nothing but individual display elements which gets lit up or gets white or dark, or it just gets vanished in the background, or it shows a different contrast with a different color. Okay, so this is a monochrome display we are considering, again very traditional and easy to understand. If you come across any display device, it comes with in 2 parts. Okay, so what are the 2 parts? The parts are basically LCD panel and its controller driver circuitry combined together. So I'll combine this driver and controller together and the panel part. All we are seeing from outside is the panel part. Okay, so we are seeing the panel part, but every panel must have a controller and a driver. So these are the backbone of any display device. So whenever we want to display something on the panel, we never have direct connection to the panel because the panel connections are quite large in number. It's basically there are hundreds of connections for every pixel. Some control signals are going between the controller and the panel through the driver. Okay, so there are hundreds of control signals available based on obviously number of pixels that you have. So in this case, it is only 40 segments are shown, but actually for every pixel there are connections from the controller to the panel. So if you keep on updating each and every bit with ones and zeros, it will be too tedious. So that's why people came up with this controller concept, which has some sort of shift register and some sort of intelligence. It's a little microcontroller actually. So that's why it is called as controller. So which is a large scale integration system, chips are used. Basically, there is a lots of hundreds of transistors, thousands of transistors actually here, digital circuitry, which reduces the overhead on the master microcontroller, which is the main processor, whether it is 8051 or in modern days our application processors like Cortex or A50, A14 kind of chips in our mobile phones, or i7 in our laptops. So the concept is still the same, only the complexity is different.
The technologies are different. So the microcontroller or which sits outside is only having certain limited number of lines to be interfaced with this controller, and then it can write to this controller. The controller will make sure that the correct things are going and displayed on the panel. And there are different pins for this 16 cross LCD module. So you can see VSS, VDD, then power supply for LCD, and also contrast control through this VO. So this is not just power supply, but this is the power supply for the panel. And also, if you change the voltage for this VO, it is going to change the contrast. So you can change the contrast on your display monitors and so on. So that's done by changing certain biasing voltage inside. So that is this V0 in this old display. Then there is called register select. So this bit is there to select different registers. So this is in this traditional LCD, there are only two registers, display and command registers. So this is just a 1-bit operation. In modern LCDs, there is no such pin. Instead, there is a softer way where 16-bit or 32-bit registers are there inside, and through which you select different registers. So in this old LCD, there are only two registers, so 1 bit high or low combination. Then read/write bar. So this is read/write bar. So there should be a star over here. So you keep it 1, it will read something from the controller to the microcontroller. If you keep it 0, it will accept, LCD controller will accept from the external microcontroller. Enable is global enable. It is just turn on and off this entire LCD module. Then there are data lines. So these data lines are 8 bits in this case, but again, modern LCDs are having more pixels, more contrast, more features. So number of bits are 16, 32, even 64 bits wide interfacing lines available. And this, out of this 8 lines, you can use it in many various modes, like 4-bit mode or 8-bit mode, complete 8-bit mode. So obviously 8-bit mode will take you less time to transfer data. 4-bit mode means nibble wise, you have to send 2 nibbles per byte to update any value inside the command register or the data register, or you can say instruction register or the data register. So I'll tell about that. Then there are connections for the backlighting. So the backlighting, so while we change the intensity of the display or the brightness level, we are actually changing the backlight power supply voltage. So this is how actually the brightness control is typically done. So brightness is nothing but backlight control. So in modern days, we use white backlighting. And earlier days, there were some different types of bulbs arrangement which were there, or different tube-like bulbs arrangement which were there to change the brightness. Now, how do we interface LCD to a microcontroller? Look at the left-hand side diagram. So 8051 microcontroller, through the GPIO pins or input-output pins, we have to connect to the proper pins of the microcontroller. So this is CLCD, means character LCD. So this LCD is able to generate only character information. Okay, you cannot draw arbitrary patterns very easily. It is possible, but it's not that straightforward. But it is mainly for character display. Now, there are pins like register select should be connected to one GPIO, and RW bar should from another one, enable from another one, and then data bus 0 to 7 from one of the buses. Look at this port assignment that I'll be considering in this example. Port 1.0 to 1.7, I'm writing LS bit first because to match up with this side, DB. 0 to 7, then port 2.0 for RS, 2.1 for read write bar, 2.2 for enable. Okay, so this is basically my choice of pins for GPIO connections. I can use other pins also, so there is no restriction. Okay, and as I said, there could be 4-bit mode or 8-bit mode. So in 4-bit mode, you can actually use only the upper 4 bits, and 8-bit mode, you can use all 8 bits, and remaining pins stay as it is. As I said, the contrast control is adjusted by changing the voltage at VO terminal, which is also acting like a power supply for the panel part of the module, LCD module. And look at the timing diagram here. So yeah, so RS and read write bar are combined together actually. So you have to set it first. So before starting anything, so how to read timing diagram? If you remember, you have to always draw some virtual lines in the vertical direction one after another. So let's say I draw a vertical line extending this red line. So I have to first initialize RS WR bar, and then I have to do other things later on. So after some time, I will enable set the enable to high. And once it is high, then I will start making the data available, whether read or write data, whichever comes site based on read/WR bar. So if I'm writing, then I have to set the I have to send this GPIO based data from port 1 in this case. While the enable is 1, but it is not an absolute necessity. This age and this age can be interchanged. That means enable come after the data valid is on. So that means you can have this logic 0 to 1 age over here, and you can totally delete this part, left hand side part. So this is possible, but this is mandatory. Okay, but this is optional. So this first and this last later, it's optional. And then for read or write, you can see read or write is happening through the same bus. Only thing is that while you are reading some data, so the timing of this thing gets slightly different than the writing operation. But more importantly, this age is important. So that's why enable is given in the black line, and I have also drawn an additional line over here, data exchange instance. That means at this particular time, we are going to exchange data, whether it is read or write. That's definitely important. But while the enable thing is coming 1 to 0, that time the data should be considered as a valid data. Okay, so that is important. And then you can see this little truth table for this RSWR. So you can see register select. If it is low, then it is always going to the instruction register or command register or status register. Okay, so while RS is low, that means you are writing some command or reading the status or writing some instruction to the LCD module, to the LCD controller part of the module. And whenever RS is high, then we are writing something to the display. So we are actually sending some data to display. And suppose we have written something to the display and we want to read it back, because microcontroller doesn't have a camera to look at the display. So it will only do the reading of data, whatever was written earlier, through some digital data transfer. And that's what this thing will happen. So when RS is equal to high, we are talking to data register, while RS is equal to low, we are talking to command/status register. Okay, so I think it's 10 o'clock now. I'll take the attendance and we'll continue this discussion. It is very interesting discussion in the tomorrow's class, and we'll complete this LCD part tomorrow. And just a small announcement. I am preparing one assignment. I've almost prepared it, and I'll be circulating that very soon. I'll give you about 1 week time to update your answers, upload your answers once I actually announce it. And there'll be class test also in addition. Okay, so I've taken the attendance. You guys can leave now or stay back for questions. So I'll stop recording now.